Thank you. So the good point to have a slide, I could show a nice picture. So the bad point with the slide is sometimes I will go a bit fast. So I will share my slide. Don't worry if you miss something. So today I would like to present convex integration in the case of one dimension. And so why I do that is because in fact the theory of convex integration is based on a one-dimension formula. So if we mainly understand what's happened in one dimension, we understand nearly convex integration because it's just after induction. So I will present the induction tomorrow, and today we'll focus on the one-dimension case. So I start with an example, which is an example of Thurston corrugation, and after we talk about the general case in one dimension. So I would like to first consider this theorem, the Whitney-Grosjean theorem, which says that if two immersed planar curves, sorry, I forget planar, have the same turning number, there exists a regular homotopy in the plane from the first curve F to the second curve G. So I just recall quickly what is the turning number. So the turning number is the number of terms of the derivative. So in fact, here we are in the case of immersion. We consider immersed curve. So the derivative never vanished. And like we have closed curve, the derivative is a closed curve which never which avoid the point 0. So we have a closed curve which avoids 0. So we could count the number of terms of the derivative. So if we compute the derivative of this one, this 0 term around the point 0, this one term, and 3 terms. And for example, following the theorem, there exists a regular homotopy between these two curves in the middle. So let's try to do this homotopy. So we want to avoid example like yesterday. So a possibility to do a regular homotopy between these two curves are this following. So okay, just regular homotopy, we just do thinking a bit 5 minutes on the front of paper, and we manage to do that. But if we don't want to do that each time. Each time we have two terms with the same turning number. We don't want to spend so many times to find a regular homotopy. So for now, the question is there an algorithm to do this easily, to find a regular homotopy really easy? So for that, let's consider the deformation of Thurston given by Thurston corrugation. So we have an initial curve at 0. We have a number of corrugation, oscillation, n. Then Thurston defines the new curve F1 given by the initial curve plus a deformation. So the amplitude of the deformation is R, controlled also by 1/n, the number of corrugation. The term in green gives the curve here, the A curve in the center. So in fact, we add an initial curve plus the curve in green, and we obtain oscillation. So this is the deformation introduced by Thurston. And let's see what happens when we change a bit parameter. So here I just consider the segment F0, which has to x in the plane, 2 corrugation. Okay, so we see there is only 2 oscillation each time. And here, so R is the amplitude, and alpha is a vector which directs, in fact, the oscillation. We see then when we change alpha, so here the corrugation is really orthogonal to the derivative. And here it's a bit, let's say, this is an angle, the angle we just introduced here in the exponential. So, okay, we start to understand a bit this parameter. So the amplitude R, which controls the amplitude of oscillation, and alpha, the vector which controls the direction of oscillation. Let's continue on the curves. So we continue. Here we have the cycle. Okay, 8 corrugation, an amplitude, okay, given by 2. And still, the vector given by the derivative. So here the direction each time are, can I say, the oscillation progress in the direction of the derivative, and the amplitude is in the orthonormal direction. So let's continue a bit. With this time, a singular curve. So I take this part of curve given by cos power 3 and sinus power 3. And this curve is singular at the point, which is x equal to 1/2. And we try some parameter, so an amplitude, and a vector, here given by -1 in the plane. And we obtain that for n equal 4 and n equal 20. And in fact, we manage to remove the singular point. And we would like to understand why this parameter allows to remove singular points in this case. So what's happening? So we consider here curves in the plane. So I work with complex number, and the 1Z space is the following in this case. So we have 0, 1 times C, and our partial constraint is, so if F is an immersion, so this it's a derivative, it's not F. So we need that the derivative of F never vanished. So the differential relation associated to this constraint is the subset of the 1Z space given by all triple, such that the component which replaces the derivative never vanished. So this is not partial differential relation. So what we have, in fact, at the beginning, we consider the formal solution sigma. So sigma is given by x or singular curves, and a vector v1 which replaces the derivative. The derivative vanishes. So we have to choose another vector field v1. So I just choose v1 equal -1. Why not? It's never vanished. I don't care. So to go back to the formula of Thurston, we just have to set alpha equals to v1. So we have this deformation, and the derivative is this one in the case of Thurston. And we have to check if this derivative vanish or not. So we have to understand this formula. So, okay, we could rewrite a bit the derivative like that. So f1 prime is given by the derivative of f0 plus what is given in the deformation. So the amplitude time an arc of parabola, I just draw there, plus an error controlled by the number of corrugations. So more the number of corrugation is large, more the error is small around this arc of parabola. So we don't know exactly why the derivative, but we are sure that our new derivative is on a neighbor of this arc of parabola. So in fact, we just have to choose our parameter such that this arc of parabola never cross the red dot, which is our constraint. Our constraint is the new derivative has to never vanish, so it has to never cross 0. So in this case, if the parameter is large enough, if our arc of parabola is large enough, then whatever happens, it's an immersion. Is it fine for now? So what's happened to build a regular homotopy? So we consider a curve, an initial curve, and we add corrugation. So we see still a bit in light blue the initial curve, and we adjust corrugation on it. And after, we do a regular homotopy, a linear homotopy, sorry, between our initial curve and the end curve. So I'm not sure it's really clear in light blue. So in light blue, we have the initial curves. We just do a linear homotopy, and we don't care about if this singular point who appears. In fact, we have two singular points which appears, one there and one between the top. But like we add corrugation, we don't care. We could remove it really easily. So a linear homotopy. And after we unravel the corrugation, so we turn it until that, and after we could remove corrugation. just pushing the amplitude until to 0. And we have our regular homotopy without thinking, just applying the algorithm of Thurston. So the aim of Thurston was not to write an algorithm for curve, it was to give a sphere inversion. So to do that, so Thurston considers a sphere at the beginning which is gold outside, purple inside, and at the end a sphere which is purple outside, gold inside. He pushes the north and the south pole, but doing that there is a singularity which appears on the equator. But you want to remove singularities, we just add corrugation on the equator. So we see here this corrugation on the equator. This is the intermediate step. So we see the linear homotopy pushing the north and the south pole, and it just add corrugation without thinking, and it just obtains a sphere version. Really will be easy.
I'm sorry.
Yeah.
Could you explain the colors? So we have the sphere, the corrugation, and then we have the violet thing, purple thing popping up. No, like the upper row.
So which part of the second row?
No, the first row.
Here?
No, not the column, the rows. We have the sphere, the corrugation on the, and then we have the violet thing popping up. Is it like the south pole popping?
Yeah, the south pole is the inside of the south pole.
Okay.
Self-crossing. Okay. So yeah, we allow the self-intersection. So that's why we have the south pole which appear in purple.
Okay, so you just pop it from the
part. Exactly. We just push the north pole. So yeah, exactly. Thanks. In purple we see the south pole. And now we are invert the south pole, we just invert after corrugation. So we unravel corrugation to put it in the good direction. And when we have the good direction, we could remove corrugation.
Question.
Yes.
If you push the north and the south pole, even if it is corrugated, you still have singularities of the equator, no?
Yeah, yes. But we remove singularity with the formula, the previous formula.
But you have, once you are corrugated,
it's not easy to see the step between the first dimension and the second dimension is not easy. I understand. I think, well, to have more detail, I just advise to watch the video and ask me again.
One very small question, but in the video it looks like in the corrugation they are turning or something like that.
Yeah.
It's not simply pushing. No?
Yeah, exactly. So here we are after the linear homotopy. So you see after the linear homotopy, the corrugation is not in the direction of the derivative. So you have to, I don't know to say, the corrugation to have in the good direction, because when you remove regularity, when you, I can say, retract the arc of cycle, you have to be sure to not cross 0. So you have to be in the good direction before removing the corrugation. So yeah, in fact, so the first line, so maybe, okay, the first image is corrugation which grow, and after the linear homotopy is maybe still on the first line, and we leave the second line until there, I guess, is really when it falls the direction, when you change the direction of corrugation. So it's really a hard step to see in 3D. Okay, so that was, yes.
So does it choose the number of corrugation?
Good question. So this is not exactly a minimal boundary. You just have to choose the number of corrugation so that the error here, controlled by 1/s, is small enough. So it depends, in fact, where is your arc of cycle. So in fact, it's a good question. Because we have to consider the arc of cycle for any partial derivative. And like it's a compact set, 0, 1. In the case of curve is 0, 1, but on the figure is also compact. So we have to be sure that this avoid 0 for any x. So for any x, we have to choose a minimal of R and a minimal of corrugation to avoid it, which is only possible, in fact, in compact set. If you have a non-compact, well, there is no minimum. Everything's fine for that? Ready for the next step? Okay. Yes.
And when we say that R must be large enough, what does it mean on the picture? Like you must have big oscillations.
So R large enough means when you turn the direction of corrugation, it could be appear a singular point. So to avoid singular point when you turn corrugation, so okay, in 3D it's still hard to see. Maybe there, you see that, okay, maybe not the linear homotopy. Here the corrugation are really a mess. It's a mess. We don't really understand what's happened. But to be sure there is no singular point, we need the amplitude is large enough. And we don't care. Everything's fine for this. Okay. So let's go for a more general formula. So we are still for curves in the complex plane. So we still are with the one jet, this following one jet space. We consider a differential relation, so just a subset of the one jet space, and a formal solution. A formal solution, so it's just a curve, and for any x, a vector, which is not necessarily the derivative, but which satisfies the differential constraint. And in fact, we want to generalize the formal approach to build an holonomic solution of the constraint from a formal one. Choose a formal solution, and we want to deform it. And for that, we consider the following formula. So for this formula, we need, of course, an initial curve to deform, a number n, which will be, again, the number of corrugation, and a way to write this deformation, to encode the deformation. And then we said just the new curve is a previous curve with this deformation. So 1 over n to control the amplitude. And the integral of the loop family gamma minus its average. And we still have the number, which is the number of corrugation. So in fact, if in the previous formula we choose the following loop, the loop gamma given by this formula, so we just it just leads to the Thurston corrugation because it's still to an initial curve. We add so this choice of loop and we obtain the Thurston corrugation with this choice. So for our new formula, what's happening exactly? So we have the following property. So we are as close as we want to the previous curve. So we have F0 here in black. And when we increase the number of corrugation, we are closer. So it's really obvious because the amplitude is controlled by 1 over n. And then the new derivative here, if we choose that the average of the loop equals to the derivative we want to modify, then the new derivative is given by something in the image of gamma. And gamma, we can choose it. So let's just prove this formula to convince you. So first, the C0 closeness. So just note that, okay, we choose a loop to encode the corrugation. So a loop is a one periodic map. So here, just a loop minus its average is one periodic map of average 0. This means, in fact, that this integral is again one periodic, so bounded. Okay, no problem. So bounded, in fact, means it's a big O of 1. So I just put this big O of 1 in the formula. And we obtain the new curve is just the previous curve plus an error in a big O of 1 over n. And now let's just take a look at the derivative. So what's happening for the derivative? So the new derivative is this one, f0 prime, plus the term inside the integral. plus, in fact, the integral of the derivative of the loop. So for the same idea of the first step, we don't care about this term because it's again one periodic, again bonded, and it's just a big O of 1 over n. So we look at this part, and in fact, we have assumed that the derivative equals to the partial, the average equals to the derivative we want to modify. So with this assumption, the new derivative is given by, well, our choice of loop plus an error of, which is a big O of 1 over n. So in one sense, we can control the new derivative we build. So let's now assume that the relation is open. So if we assume it's open, we don't care a bit of the error on big O of 1 over n, because if n is large enough, we can reduce this error as we want. So okay, since so if n large enough, the image of gamma, if the image of gamma satisfies the constraint, that means the derivative of the new curve satisfies also the constraint. So this is what we want. So precisely what is mean. So in the one jet space, it means that the triple here, x f0 gamma x of something, satisfying the constraint implies that the triple x f0, the new derivative, satisfies the constraint. But here we are still f0. We are not yet the one jet of f1. And now we use the other property. The other property is the C0 closeness between the new curve and the initial curve. So using the C0 closeness between these two curves, now we have, in fact, and as the relation is open, we have the one jet of f1 lies in the partial differential relation. Is it fine? And also for the following, I just want to recall that to use the property of the corrugation process, we also need that the average of gamma equals to the derivative we want to modify. So we have two conditions on the loop family. One condition on the average, one condition on the image. So let's take an example. So we have a relation and we have a curve whose derivative lies in the convex hull of the relation. So we have just the derivative there. We consider a point. So okay, on this point x, we have f0, the derivative of f0, and we have to choose a loop for this x. Okay, we consider this slice. The slice of the relation here is over x is given by any value the derivative can take. So we consider any value possible for the new derivative. And now we have to build a loop satisfying the two constraints. So the two constraints is the loop lies in the slice of the relation, so satisfies the constraint, in fact, and the average of this loop equals to the derivative we want to modify. So here we have we could do this choice, and more generally, in fact, this we could choose such a loop in the case that f0 prime belongs to the convex hull of the slice of the relation over x. So this is why it's called convex integration. So it's because of the assumption of convexity on the slice of the relation. So let's go back to the relation of immersion. So here I put in blue again the slice of the relation. So the relation is just avoid the point 0. So everything is a slice of the relation. And well, the convex hull of C except 0 is the entire space. So here the convex hull is all the plane. So F0 is, of course, F0 prime is in the convex hull. So we could use the the corrugation process to build a nomic solution. And not, in fact, the relation such that the convex hull of the slice is all the space is usually called M-pole. So we will see in the next lecture in higher dimensions. And just maybe you have question before I go to this question about the previous slide. Okay. So let's continue a bit about Thurston. So Thurston built this homotopy, regular homotopy, sorry, between two planar curves. And here the corrugation are directed by a family of vector alpha x. And in fact, such that at each time, alpha x lie in the relation R. So in fact, to do the previous construction, we need to find family of vector alpha x such that at the beginning we have alpha 0 equals to the derivative of the initial curves. At the end, the vector alpha 1 equals to the derivative of the final curve. And such that for any t, alpha t never vanished because it plays the role of our new differentials of the formal solution. Sorry. So a regular homotopy is only possible if there exists such a family of vector alpha t, which never vanished. And this means that there exists a homotopy of formal solution. Sorry. So this regular homotopy is only possible if there exists a homotopy of formal solution between the two holonomic solutions G1F0 and G1F1. So the formula of deformation is stable, in fact, in the literature. We see a Thurston corrugation, we see a corrugation process. This is also the formula of Nash at the beginning in the case of the relation of isometric map in codimension 2. So Nash used an helix for his deformation to increase length. So here we have a picture for curves. This is also over deformation when Kuiper increase the result of Nash for isometric map, but in codimension 1. So we remove the helix and use the kind of wave given by this formula. So we saw the Thurston formula for the relation of immersion in codimension 1. This is also a formula in codimension 1 for the relation of isometric map by Conti, de Lelis, and Zekeleidi. Even that, I just show you they exist plenty formula. So in particular case, and in fact, in the convex integration theory, Gromov used this following formula. So where the new curve is given by the starting point of the previous curve, and just integrate following a loop family until x. And in fact, this the Gromov formula is equivalent to the corrugation process up to a big O of 1 over n to this one, which is, well, the one we just saw previously. And these both formula need, in fact, so a condition of the array of the loop family and a condition on the image of the loop family, and we could use convex integration theory. So following what you want to do, maybe one of these formula could help you. No problem. So I just had the references in my slides. If you're interested, attend them. And thank you.
Any question?
This picture.
Good question. These two corrugated curves, in fact. So one in pink, one in blue. It's when I try to remove the singular point of the cone. So the cone is here like a family of cycle, and we had a corrugation on each cycle. So you have a big cycle really far away from the singular point. And when you come closer and increasing the corrugation, you have this little distribution.
But I think it was the slide just before this. You said both formulas, the convex integration and the corrugation process needed to satisfy the same constraint. So what I don't see a gamma x in the Gromov formula. So is it so like the average of what? Is it the average, I guess, of gamma? The second formula, there's a gamma x. First formula, no gamma x. So I'm wondering.
So it's in fact, for any x, we choose a loop. So we have a loop family, parameterized by x. But here in the Gromov formula, the parameter you see s, in fact, is in the integral. So s have to cross all the set until x. So you integrate this parameter at the same time that the parameter of the loop. So you have to imagine a surface, I mean, where each time it's a loop, and just take the diagonal. So maybe I draw something. So in my previous slide, I take gamma x like it. So imagine we do this for any x between 0 and 1. So we have I don't really want this. So you have this family of loop. I mean, for any x, we have a loop in our cycle. And in fact, in the integral of the Gromov formula, the integral, if you want, I could write it like it. Sorry, s. So in fact, in the integral, you go like it. So you have a surface, and the integral forces you to go in this direction. Kind of, I don't want to say the diagonal, but the diagonal of slope.
So when you say average, is it the average of that function gamma of s comma ns?
So when I say the average, in fact, it's only here that it's one periodic. Here we don't know because it depends on your initial curve. If your initial curve is not periodic, this has no reason to be one periodic. So you can only take the average on the one periodic part. So the one periodic part is when you do a loop with the slice, and the slice is for a fixed x.
Thank you.
In the sphere eversion picture, so you had like immersion, you had like the minus of that immersion, you like joined the north and south pole, and you removed the singularities by your corrugation, correct?
Yeah.
So suppose I try to do this naive type of thing, say just for the circle, I should not be able to do it. But say I try to join opposite sides of the circle, and then try to remove the singularities by the corrugation, what would fail? So
in which
circle, like I have an immersion and I have minus of that immersion. I try to join them by some linearized homotopy, and I try to remove the singularities by corrugation. What would fail exactly?
So it could fail if you don't manage to find a formal solution, for example. If you have no formal solution, you can use it. If you have a formal solution, you could every time use that, because the relation of immersion example satisfies the constraint to use the formula. So in fact, the idea of the convex integration is push the problem until a topological point of view. So you have at one time a differential problem, and you change it in a topological problem. So you are in the 1Z space, and you check if there exists a formal solution or if there exists a homotopy between formal solutions. So looking for a homotopy or looking for a formal solution is a topological problem. So for example, if you take a sphere on the torus and you want to push a sphere to a torus, you will never find a formal solution between two because this is removal. every time singular point, so you can't use, you can't find vector to direct aggregation, which never vanish. Maybe I will talk about it further. So the condition for curves is avoid 0 if you have the derivative of f0 prime to do one term and f1 prime to do two terms. How do you find the homotopy between f0 prime and f1 prime without crossing 0? Is the equivalent question. It's easier to get that. It's a topology.
The complex integration method also gives you a weak equivalence between formal solutions and polynomial solutions.
So, yeah.
I'm asking if the convex integration method is, if I get the idea in this talk, you just use it to produce solutions that can be upgraded to show a weak homotopy equivalence.
Yeah, so I don't talk about it, but yes, there is a homotopy between the formal solution and the Riemann solution you have at the end. So you have the deformation is only in the section of the relation. So you have a homotopy between, inside the section of relation. So we have the H principle. This is a homotopy somewhere. And these over, how can I say? H principle with parameters, so you could have a homotopy between a formal solution and a Riemann solution, but you could also have a homotopy between different homotopy. Different homotopy with formal solution at parameter again.
No question. If there is no more questions, so let's thank once again our next we have coffee break, I guess. Okay.